Now having done the basics of S parameters, now we will see the mathematical basis for Smith chart, what exactly a Smith chart is and how it is really a helpful tool in analyzing various microwave circuits as well as antennas. So now let's start with the mathematical basis of the Smith chart. Now let's go to the basic thing, a reflection coefficient. As I have shown earlier, S11 or S22 defines the reflection coefficient, that is B1 upon A1 or B2 upon A2 when you have a match condition at the other port. So reflection coefficient plays a major role in any microwave circuit design because that talks about the mismatch which is there in the circuits. Now Smith chart basically plot this reflection coefficient because remember, in microwave or in RF, absolute value of the impedance is not important. What is the degree of mismatch of that impedance with reference to your characteristic impedance matters a lot because that decides whether the efficient transfer of the energy is happening or not over the microwave circuits. So definition of reflection coefficient is something very important for us. Now this I have written a normalized equation. Ideally speaking, here reflection coefficient equation goes like this. Gamma is equal to ZL minus Z0 upon ZL plus Z0. This is the reflection coefficient equation. This is the load impedance against the characteristic impedance. Now why we do normalization? Remember, normalization in this case, what we do, we divide numerator and denominator by characteristic impedance. So in that process, what we get is ZL upon Z0 minus 1 upon ZL plus Z0 plus 1. So this is the normalization process what we have applied. So this term we call this as a small ZL. This term what we call as a small ZL which was there in the earlier equation. So I will rewrite this equation as small ZL minus 1 upon small ZL plus 1. So this is the reflection coefficient equation with respect to the normalization. Now why normalization? Now what happens is Smith chart is a tool which is used for all different microwave circuits. Now there the characteristic impedance or the reference impedance of the circuit what you are using can be anything. In fact in microwave we do have sometimes characteristic impedance is equal to 50 ohm. In some cases we do have a reference as a 75 ohm or in some cases maybe the reference can be as high as 300 ohm. So in such all different reference impedance level our the plot each should be the same. Because what matters to us is what is the degree of our impedance under consideration, degree of mismatch with respect to the characteristic impedance. So in regard to that, in assessing that degree of mismatch, we need to have a normalization with respect to the characteristic impedance of the reference circuit or the circuit under consideration. So since we have different values of reference impedance used, of course in most of the time we use 50 ohm impedance only. But in some circuits, in some application, we do have a different characteristic impedance. So to have the calculation on the common platform, to have a same tool of assessment for different reference impedances, we have a normalization procedure being employed. We have a normalization procedure being employed. So we use a normalized value. In fact, if you see on the Smith chart later, you will never see 100 ohm, 200 ohm likewise. They are all normalized. They are either 1, 2, 2.1, 2.2 like that. So they are normalized with respect to characteristic impedance. Why? Because our reference is characteristic impedance. Always we assess the degree of mismatch with respect to the characteristic impedance. Being a reference, we do the normalization. So this is the requirement of the normalization. So we are going to use this term ZL minus Z0 upon ZL plus Z0 as our reflection coefficient equation. Now remember, this is a complex number because ZL will be a complex because your ZL, capital ZL also will be a complex. Now one simplified approach what we are using here, we are using a lossless transmission line. Okay, I am going to explain the procedure for a lossless transmission line, and because of that, even my ZO is a real number. What is ZO? It is characteristic impedance of the line. It becomes L by C. If you just recall transmission line basics and everything, there that R and G term vanishes, and you have a ZO as a real term. So we have a L by C as the equation for ZO. So that is a real number, but ZL can be imaginary. So reflection coefficient is becoming a complex number. So it will be in the rectangular form, it will be R plus Jx or R minus Jx. Gamma R plus J gamma I, or gamma R plus or minus J gamma I. So this will be the reflection coefficient. And just write again, ZL is equal to R plus Jx, R plus or minus Jx. So gamma will be equal to gamma R plus or minus gamma I. So this is the nature of the reflection coefficient which is there, and because of that, gamma will be some magnitude and angle. So gamma also will be expressed in some magnitude and angle. That is the reflection coefficient. So this is all about the reflection coefficient. Why? First of all, normalization is done. Then whether reflection coefficient is a real number or whether reflection coefficient is a imaginary or a complex number, and how we represent reflection coefficient. So we either represent them in a rectangular form or we represent them in a polar form. So now let's go back to the mathematical analysis of the Smith chart, what we were doing with. So I hope this is very clear to you now. Gamma is a complex number where we are plotting the reflection coefficient over there. So this is the equation for the reflection coefficient. I can expand this because I can put the values of Z here. It is basically, as I have shown you earlier, Z is R plus or minus Jx. So I am just substituting that, so you get the equation for the reflection coefficient. Here U stands for gamma real, V stands for gamma imaginary. So what we are doing in this process, we are actually converting the Z domain or the impedance domain to the reflection coefficient domain. Okay, we are converting the impedance domain to the reflection coefficient domain. Now what are the limits of that? Remember, Z domain spans over 4 quadrants. You have first, second, third and fourth quadrant. In the second and the third quadrant, R is negative, that is resistance is negative. Whereas in the first and the fourth quadrant, resistance is positive. In the initial part of the Smith chart, we are only going to deal with the first and the fourth quadrant, or we are going to deal with the positive resistance Smith chart. Okay, positive resistance chart, what we are going to deal with. There is another Smith chart which exclusively deals for a negative resistance calculation, and we call that as a compressed Smith chart. So compressed Smith chart details and everything we will see later. In the current Smith chart analysis, we are only going to deal for R greater than 0, to be very precise, or R equal to 0. So second and third quadrant we are not going to deal with right now. We are only going to deal with the first and the fourth quadrant. So we are going to deal with the positive impedance. Imaginary number can be positive or negative, because in this region imaginary is positive, in this region imaginary is negative. So we are converting first and fourth quadrant to the reflection coefficient domain. Now let's see the limits. Let's see the limits of this impedance domain against the reflection coefficient domain. So here we see R varies from 0 to infinity, whereas X varies from minus infinity to plus infinity. These are the limits of R plus or minus Jx. Then how gamma varies? Okay, so the limiting conditions are infinity and short circuit. That is the limiting condition. So if Z is equal to 0, it becomes a short circuit condition. Okay, because that is the extreme point over here. If Z is equal to 0, then it becomes a short circuit condition. That means gamma is -1 for that. And if z is equal to infinity, that means it can be positive infinity anywhere. It is a very large number, so I consider that as an infinity. Forget about the imaginary and real part in that. It is an infinitely large number. So if z is equal to infinity, then gamma becomes positive 1. Okay, gamma becomes positive 1. How you get that? You just divide numerator and the denominator by small z. So that gets cancelled. You get positive 1. So what are the limits of gamma? So if I vary ZL from 0 to infinity, gamma varies from -1 to 1. So going from short circuit condition to the open circuit condition, your gamma only varies between -1 to 1. So these are the limits. So I will say mod gamma is less than or equal to 1. So this is the limits, or this is the variation of the reflection coefficient happening for the variation of impedance from 0 to infinity. Because these are the two bounds, I will say. These are the two bounds. So what is there? Let your z domain vary from 0 to infinity. Your gamma domain only varies from -1 to 1. So if you just go back to that distribution over here, this chart, which is infinite in nature, gets converted into this UJV chart, or I will say gamma R and gamma I chart, which lies between -1 to -1. Okay, so the infinite domain of the impedance plane is getting transformed into a finite domain of reflection coefficient plane, which is mapping from -1 to 1 or 0 to 1 if I consider the mod value. So this is the beauty of Smith chart, or this is the beauty of reflection coefficient analysis. Let your impedance domain be infinite in nature. We have a finite domain or finite range to play with. Okay, and you will see later there exists a one-to-one mapping. Means what? All the points which are there on this impedance domain, they get mapped to a unique point on the reflection coefficient domain. There is no one-to-many or many-to-one mapping happening from impedance domain to the reflection coefficient domain in the Smith chart. Okay, so now that process is called, I will not get into the mathematical analysis of this because you can refer the book. We will just understand there is one important term or important equations which are there. It is called as a parametric reflection coefficient equation of the Smith chart. Okay, so it basically helps you to transform. It basically helps you to transform your impedance domain, that is the first and the fourth quadrant, to the reflection coefficient domain. So that is process is called as the parametric reflection coefficient equation. So what it does, it maps a point, each and every point from the z domain to the reflection coefficient domain. Now this procedure is somewhat similar, okay, to the calibration aspect. Because those who have used vector network analyzer, you actually do the calibration process initially. You have three reference impedances. You have a short, you have an open, and you have a match. And according to that, the various circles in the Smith charts are drawn. So this process of transformation of the impedance domain to the reflection coefficient domain is very similar, okay, to the calibration process what happens in the vector network analyzer while drawing the Smith chart. Okay, so these are the two equations which are there, which helps you to transform entire impedance domain to the reflection coefficient domain. So these are the two equations. Now these equations are very similar to the equation of the circle. Now we'll understand them one by one. Okay, this is a beautiful process which actually goes on in transforming the impedance domain to the reflection coefficient domain. So here again the derivation of this, you can refer the book, because for understanding purpose, derivation of how these equations have come is not important. There is a derivation which is available, so you can refer. But how this process, how this transformation occurs, that is very, very important. So this is the equation for transformation of a real part into the reflection coefficient domain. Now it doesn't mean that R has a only role to play on gamma R. It has an effect on gamma I because it is a combined quantity. So this equation transforms different R planes to the gamma plane. Okay. So now let's see one by one. When r is equal, in fact we'll select one by one and then we'll select the complex point, that is combination of r and x. So for r is equal to 0, if you just put r equal to 0 over here, this becomes the equation which is written over there. Now r equal to 0 means what? We have a short circuit plane, okay? But short